dear students, I have started the chapter solutions, and in the first period I have given you what are solutions. Solutions contain solute and solvent. Generally, the substance which is present in small amounts is called solute, and the substance which is present in large amount is called solvent. Okay, we have different types of solutions. A solid in solvent, or you can say liquid also. This is one type of solution. Liquids. Gas, liquid. Gas. So these are the common types of solutions. A solid is dissolved in a liquid, liquid in liquid, gas and liquid. These I have given you in the last class. Sucrose solution or glucose solution. Sucrose solution or glucose solution, liquid plus liquid, alcohol plus water, and gas liquid, let us say ammonia water. So ammonia gas is dissolved in water. So these are the examples, important examples for solutions. So a solution mainly consists of a solute and solvent, and the substance or the component which is present in small amounts is generally referred to as solute, and the substance which is present in large amounts is known as solvents. Okay, and in solutions we have different types of solutions. So here I have given only three types: solid, dissolved in liquid. The example is sucrose solution or glucose solutions, or even salt solutions. Liquid, alcohol and water. Okay, benzene toluene is also the example of liquids, and gas liquid, ammonia and waters. And these again we have among the solutions we have ideal solutions and real solutions or non-ideal solutions. Real solutions or non-ideal solutions. So what is an ideal solution? An ideal solution is one which obey Raoult's law at all temperatures and concentrations. So this is the general rule for an ideal solution. An ideal solution is one which obeys Raoult's law at all temperatures and concentrations. This is the first condition. Second condition I have already given you: the change in volume upon mixing the components should be equal to 0. Similarly, the change in enthalpy upon mixing is equal to 0. Here what are we mixing? You are mixing two components. One is solute and one is solvent. Okay? And in this chapter I am mainly concentrating on liquid solutions. Liquid solutions I am talking. So a solution is said to be an ideal solution if it obeys Raoult's law at all temperatures and concentrations. Similarly, the change in volume upon mixing the two components should be equal to 0. The change in enthalpy upon mixing should be equal to 0. Similarly, the activity of any component should be equal to mole fraction of that component, where I is the component. Okay, so these are the four conditions that are essential for an ideal solution. The activity of any component. Here I have taken two components. You can take either this component or let us take liquid A and liquid B. Let us take liquid A and liquid B. Then you can write here. The activity of liquid A should be equal to mole fraction of the liquid A. This condition is also required for an ideal solutions. Okay, next, what is Raoult's law? That also we have discussed it already, but let me tell you once again. It is given by the partial vapor pressure of any component, where A I have taken as the component. Okay, the partial vapor pressure of a component say A should be equal to the product of mole fraction of this component, and the actual vapor pressure. So this is the Raoult's law equation, and the definition is like that. The partial vapor pressure of any component, say for example component A, is equal to the product of mole fraction of this component and its actual vapor pressure. This is the partial vapor pressure, this is the actual vapor pressure. So this is the definition of the Raoult's law, and this is the expression of Raoult's law. Okay. Similarly, if we take the component B is equal to xB into A0B. So this is the expression of Raoult's law for component B. Next, what is mole fraction? Mole fraction is for a component x equal to Na by Na plus Nb. So if you take a solution containing two components A and B, then mole fraction of A is equal to number of moles of A divided by number of moles of A plus number of moles of B. Similarly, the mole fraction of B is equal to number of moles of B and number of moles of A plus number of moles of B. So this is the expression for mole fractions. So this is about the ideal solutions. And if you see the thermodynamic relations, thermodynamic properties of solutions, you can easily write. First one is, I told you, Ai is equal to Xi, where I is a component. Okay, this is one thermodynamic relations. So this can be used to calculate free energy change. The free energy change upon mixing is equal to nRT ln Ai plus nRT ln Aj, where I is one component and J is another component present in the solution. If you want, you can take AA plus AB. Okay, if the solution contains component A and component B, then this is the equation, thermodynamic equation for change in free energy upon mixing A and B. A and B. This is one thermodynamic properties, that is change in free energy. Similarly, I told you the change in volume upon mixing is equal to 0. This is one more thermodynamic properties. A change in enthalpy upon mixing, this is also equal to 0. This is another thermodynamic property of the solutions. Then the change in entropy, upon mixing is positive value. So these are the thermodynamic properties of the solutions. Thermodynamic properties of solutions. Okay, we have four: change in free energy, change in volume, change in enthalpy, and change in entropy. Delta X axis is always a positive value. I mean, it is always greater than 0. It is always greater than 0. So these are the thermodynamic properties of the solutions. Ideal solutions. Ideal solutions. Now we shall come to the real solutions or non-ideal solutions. What are real solutions or non-ideal solutions? These are the solutions. These are the solutions which deviate from Rolle's law. They do not obey Rolle's law. They will deviate from Rolle's law. Such solutions are called non-ideal solutions or real solutions. We can also give the examples for ideal solutions. You can have the examples for ideal solutions and examples for real solutions or non-ideal solutions. So that you can see the textbook and you can write some examples for ideal solutions and non-ideal solutions. Now I shall do the behavior of ideal solution. If you take a diagram, it is the composition and it is the vapor pressure. So this is the vapor pressure composition diagram of an ideal solution. Ideal solution. If this is A, component A, and this is component B, then you can write a Rolle's law for this equation. The Rolle's law for this equation is PA is equal to XA P naught A. This is the Rolle's law equation for component A. Similarly, for component B, PB is equal to XB into P naught B. So this is another expression. PA is equal to XA P naught A. This is the Rolle's law expression for component A. This is Rolle's law expression for component B. And this is the total vapor pressure. Total vapor pressure. Total vapor pressure is given by PA plus PB. PA plus PB. So this is the equation to get the total vapor pressure. So this is the diagram for an ideal solution. Which now, if you come to the non-ideal solutions, we have three types. We have three types of non-ideal solutions. Type 1. Type 1, where these solutions deviate slightly from ideal behavior. ideal behavior. Positive deviation. Deviate slightly positive from ideal behavior. That is the first type that I will show here. So this is the ideal behavior I have already given you. Now, if you consider the non-ideal solutions, under this heading, the first type non-ideal solutions have slight positive deviation from ideal behavior. So this is the ideal behavior for the solution. This is the for component A. This is for the component B. Now, positive deviation, slight positive deviation. Like this. This is the slight positive deviation. For this one also, slight positive deviation. This also slight positive deviation. So there is a slight positive deviation from the ideal behavior. This is the ideal behavior. This is the deviation. This is the ideal behavior. This is the deviation. This is the ideal behavior. This is the deviation. This is the slight positive deviation. So this occurs in the type 1 non-ideal solutions. If you come to the type 2, if you come to the type 2 solutions, there is more positive deviations, more positive deviation from ideal behavior that I shall represent here. So this is the ideal behavior I have already given. This is the ideal behavior, ideal solution behavior. Now I am going for the type 2. Type 2 non-ideal solutions where we have more positive deviation. More positive deviation from the ideal behavior like this. This is the more positive deviation. Okay? And here also more positive deviation. Here also for this one. For this one also we have more positive deviation. So this is the type 2 solutions where the non-ideal solution has more deviation towards positive side. Such types are called type 2 non-ideal solutions. And lastly, we have type 3 non-ideal solutions. Type 3 again we have more negative deviations. More negative deviations. So this is more positive. Now we have more negative. More a negative deviation. So it is like this. This is 1. This is for this one. This is for this one. So there is a negative deviation. So if this is the ideal behavior, this is the negative deviation. Okay? If this is the ideal behavior, this is the positive deviation. Type 2. This is the type 3. And if this is the ideal behavior, there is slight positive deviation. This is type 1. Slight positive deviation type 1, more positive deviation type 2, and more negative deviation type 3. So these are the 3 types of non-ideal solutions or real solutions. Okay? As I told you already, you can give some examples for non-ideal solutions and some examples for ideal solutions. In the next class, I shall go for the fractional distribution. Fractional distillation. this I shall discuss in the next class. Okay? Okay, thank you.